Welcome back, Calculus BC students. We've finished our short expedition into parametrically defined equations, and now we're actually coming to the second part of topic 4 out of our parametric vector and polar equations. Parametric and vector, I would say, take up about a third of this, and then polar is really that I don't know, maybe that main focus. So we're going to save that for the end. And we're going to do probably the worst job ever in discussing vector-valued functions. Maybe as poorly as a job as we did with parametric functions. So parametrics, vectors, and polars, as a reminder, are concepts that you should have learned in pre-calculus. However, I understand that it's been a weird couple years. You might not have learned it, depending on your curriculum, and that's okay. Really, if you want to learn a bunch about vectors, you should probably take a couple intro to physics classes or watch a few Khan Academy videos. They do a pretty nice job. But the general idea behind a vector is given as a magnitude and a direction. So if you had some sort of xy axis and you said, okay, we're going to have you start at the origin, and then we're going to give you a magnitude of 3 and a direction of 40 and a direction of like 45 degrees if we're thinking in polar mode. So we'd look at 45 degrees, and then a magnitude of 3 means this arrow would point out for a length of 3, and then there would be a point at the end. Okay, so this vector is pointing to the point, but the vector itself is actually the arrow here. Now, vectors and parametric equations are super closely related. In fact, for our purpose, they're essentially the same thing. Now, a vector-valued function or a vector-valued equation is going to be an equation with multiple components, just like a parametric equation. We're only going to have 2 components, an x and a y, but as you move further on to mathematics, you'll have 3, 4, or n dimensions coming out of this. And they are really just going to tell us how to get to this same arrow that I drew up here, except instead of doing a rotation, they are going to say go x some amount and then go y some amount, right? Vectors. Very exciting, really useful, lots of cool properties. We just don't have time to get into it for now. Individually, these components are parametric equations like x of t and y of t. Now, the difference, I'd say maybe one of the main differences with vectors is vectors aren't always starting at the origin. So technically, this blue vector that I drew here, if I were to draw another one that is up here, like so, and said that's 3, and I was considered starting over here, and this was 45 degrees, this vector is technically equivalent to this vector. They are the same length, and they have the same direction with respect to wherever I started. And so that can get a little bit tricky. So all we're going to be dealing with are what's known as position vectors. And position vectors are always defined as starting at the origin. Okay? Our position vectors are going to have 2 components, an x component and a y component. Our velocity vectors will have 2 components as well, the velocity in the x direction, the velocity in the y direction, and the same for acceleration. These are going to be describing planar motion, right? Motion through a plane. You can do this through an nth dimensional plane. However, we are only going to be doing it through a 2-dimensional plane, as opposed to what we did in Calculus AB. Calculus AB, we talked about equations that defined particle motion to the left or to the right, and we usually called that equation x of t, or vertically, up and down, and we usually called that equation y of t. So now we're actually going to put it together, and instead of particle moving like that, we could have some sort of particle moving in a wave, a curve, as long as we're moving through 2 dimensions. Alrighty, so some definitions. If you are given a particle moving along a smooth curve C, then at some time, t is going to stand for time in all of this. We're going to let x of t represent the position of a particle in the x direction and y of t in the y direction, and then we're going to define this vector notation down here, s with an arrow, traditionally only with the arrow having this top little piece like that instead of both. Or, more commonly, because this is a little bit more obnoxious to type, you will see vectors in bold. If you see a bolded lowercase letter, then it means it is a vector and contains multiple components. In this case, the vector s of t contains components x of t in the x direction and y of t in the y direction. And when you put those together, s of t is going to map a particle that goes in some probably curvy direction. And I know that's not very mathematically accurate, but I think you get the idea. Okay. So I've tried to bold my vectors as I go throughout here, mostly in sheer laziness, and I didn't want to put the little hat on the top, but maybe one year I'll go back through and change that. Now, we discussed in parametric equations that dy dx becomes a little bit complicated, and that's due to the attempt to combine the x and y components into a single equation, because this parametric equation is one equation that just has multiple parts. Luckily, derivatives for individual vector components are way easier, because vectors are all about keeping the components separately. So if I wanted to find dv dt, and you're going to see it with respect to t here as opposed to dy dx, right, then it just means take the derivative of each individual piece. So take the derivative of the x component with respect to t, take the derivative of the y component with respect to t, and leave them right next to each other. The acceleration vector, same idea, just find the second derivative. So way more straightforward, nothing too terrible. We do have probably a couple more formulas to look at, but you're going to see a lot of similarities to parametrics. And you might say, well, what if I confuse them? They will be stated in a way that you won't confuse them. There will probably be one or maybe two questions about parametrics and vectors. I will say that these vector functions are more common than parametrics, and it is usually one full free response that's either talking about vectors, and you can think of vectors as like particle motion, same idea, or the free response will be about polar. That's been pretty common in the last probably 10 years or so. Remembering that our free responses, there are 6 of them, 3 of them are A-B topics, so nothing we've covered this year. That's why you're doing all that review. And then out of the other 3, the 6th question, so that brings us up to 4 total, right? Maybe I should do it like this. 3AB, and then question number 6 is always BC, and it's always series, at least it has been. It could change, right? So there's 4 questions. And then out of the other 2, so we'll call them questions 4 and 5, though they don't go in that order, one of them is usually either a vector or polar question. And then the last one I call a wildcard question. I mean, it could bring in, what else have we done? It could bring in some maybe series tests, something like that. It could bring in partial fraction decomposition. There could be something about, we'll learn this in our next unit about logistic curves or Euler's method, but yeah, definitely a wildcard. But those ones are pretty darn predictable. 3 ABs, who knows what that'll be. 1 either vector, meaning our particle motion or polar, and then 1 about series. So definitely good that we're getting this one out of the way first so you can start practicing those free response questions. We're going to do a whole bunch of practice today, and again, there's nothing too much new. I think you'll find this one fits pretty smoothly into your current understanding of particle motion. There were 2 other things that we had to do in particle motion, and the first is, and this is always the trickiest one for all my students in AB, is to find the speed of a particle, right? Now, in AB, what you would do is to find the speed, you would find something like, we would say that speed is the absolute value of velocity. So in AB, you would take the absolute value of velocity and you would set it equal to whatever speed they were asking you about. Alternatively, you could have said something in AB like v of t equals the positive number, or v of t equals the negative number, and then solved each one of those. However, that's only moving side to side or up and down rectilinearly, right? However, once we get to 2 or more dimensions, things get a little bit more complicated, but it's really the same formula, right? We just need to remember that if we're going to find speed, it is still the absolute value of velocity. But in a vector situation, the absolute value of velocity, or the absolute value of a number, is really measuring the magnitude or the length of that. So if we think back to an xy axis over here, and we think that our velocity vector, so the vector pointing the direction in which your particle is traveling, and again in AB it would either travel to the left, right, or it would travel up, down, but now that we're in BC, we're in 2 dimensions, this particle is traveling this way, right, traveling at a diagonal angle. If we want to find the length, because absolute value measures the magnitude or the length or the distance from 0, right? We want to figure out how long this is to figure out how far away from 0 we are. That's what absolute value does, right? The distance from 0. Well, we already know how to do that. This is just the Pythagorean theorem, right? dx dt in this case is telling you the length of the bottom triangle, and dy dt is telling you the other leg of your triangle. And if you would like to find this missing side up here, it's just a matter of a squared plus b squared equals the length squared, and to isolate the length we just take the square root of everything. And so we can define the speed as this guy, the square root of the velocity squared plus the velocity squared, but it's really the velocity in the x direction plus the velocity in the y direction. And the nice part about this, once we see the pattern, is first, this does work for AB stuff, right? So we have this, and you're like, but in AB this doesn't help. Sure it does. In AB you only have one of these, so let's get rid of that. And then those cancel, and it shows you that the velocity is the derivative, right? Nothing bad there. You just have to remember how to solve an absolute value equation. And the really cool part about this is now we can extend this to multiple dimensions. Let's say that they wanted you to find the length of the velocity, the speed of your particle in 3 dimensions. Now if we have a z-axis, well, you just tack on one more, and we have a 3-dimensional Pythagorean theorem, which is very strange to wrap your mind around. But either way, same idea. Math is all about patterns, and once we can start to see the patterns, we can do more. All right, and I should mention you do need to memorize this formula. Cool. Last but not least, the only other new part of today is you need to know how to find the distance traveled by the particle. However, we can already do that. That's the same thing as parametrics, right? They're very, very similar, and we learned in parametrics we get this piece here. I should be a little more specific here, and I should probably update this for next year. These right here are going to be equations. They will have t in them. However, this is a value, and so maybe I should do that down below. This over here, though, is a value. So really what each of these are saying is if you're looking at v of t, then each of these are being evaluated at t equals some number and evaluated at t equals some number. So it should make sense that they're like, find the speed of the particle, and you find an equation. You have not found the speed. So yeah, we do need to evaluate this at whatever number they're asking you about, versus this one, you're using equations and finding the area underneath those equations. Cool. So, some practice should not be too awful. Let's begin. A particle moves in the xy plane so that at any time t, the position of the particle is given by the x component and the y component put together. Find the velocity vector when t equals 1. Well, the vector, notice this bold again, the vector that describes the velocity, that shows what angle this is traveling at, just puts together the x component and the y component so that we can find the overall angled component. And to find the velocity, if we are given positions up here, I think we probably just need to take the derivative, right? It's that easy. So we'll go blue and green here. So the derivative of x gives us 3t squared plus 8t, and then we need a comma. And then we need the derivative of our y component, 4t cubed minus 3t squared. Looks pretty good. And last but not least, we need to find v of 1. So substitute 1 into each component. 3 and 8 gives us 11. And 1 over here, 4 minus 3, gives us 1. Therefore, the velocity of 1 is defined by the x distance of 11 and the y distance of 1, which shows us, if you wanted to think about this graph, right, here is 11 out here, here is 1, that our particle is moving with a velocity is being pushed in that direction. Then find the acceleration vector of the same position for the particle when the time is 2. Well, this is just the second derivative. We'll use those same colors. Second derivative of this guy over here is 6t plus 8. And over here, it's looking like 12t squared minus 6t. And then we have to find the acceleration at 2. Okay, so if we substitute in 2, 12 and 8 gives us 20. and substitute 2 in over here for 48 minus 12. Who made this problem? That's too much mental math. 36. Awesome. And so what does that tell us at 2? It tells us it's accelerating a little bit more in the upwards direction than to the rightwards direction. I'm sure that's a word. And yeah, there we go. Particle motion in 2 dimensions instead of 1. It's exactly like 1 dimension, except you put a comma in between and do twice the work. Okay, second out of 3 examples. We have a particle moving in the xy plane. They tell us that time is greater than or equal to 0. Very common setup. We usually don't look at things with negative time because we always define a time of 0 as when we started observing it, and how can we say things before we were observing. They give us the position, find the speed when time is 1. Well, we do need to keep remembering that speed is the absolute value of velocity. Very important. Okay, and that means the magnitude of our vector. This is just the Pythagorean theorem. So what do we need to do here? I'll try to continue with these colors as we go through. We take the derivative of x, 2t plus 3, and the derivative of the y component, 3t squared minus 6t. And ultimately, again, if we want to know the speed when t is 1, then this should probably be better defined as the speed of the particle at 1 is, and then it's going to be dx dt evaluated at t equals 1 squared plus dy dt evaluated at t equals 1 squared. So this is a number being squared and a number being squared, so we should probably find those values. Dx dt of 1, or evaluated at 1, 2 plus 3 I think gives us 5 there, very exciting. And at 1 here, 3 minus 6 is negative 3. Cool. So I think that gives us this guy down here, right? We're just substituting each of these values into our equation, and the rest is very easy. So not the velocity, but the speed at 1 is found by the square root of 25 plus 9, square root of 34. It looks like it should be 36. It's not. It's 34, and we are good. 17 and 2 prime numbers, can't break it down. Last but not least, I really liked this question. I've seen something similar on free responses in the past. They really like to throw out the, what happens at an intercept, just to make sure you remember how to find intercepts. So let's parse through the problem. Particle moves in the xy plane. We, of course, have our x component over here. Uh-oh, they have cosine and sine. Who chose this problem? Where t is from 0 to 2 pi. It's my guess, based on cosine and sine, if you were to graph this, we're probably traveling in a circle. The path of the particle intersects the x-axis twice. Well, that still kind of holds to what I'm thinking. My guess is our particle, and I'll show you this in vectors, probably does something like this. Maybe, at a t of 0, maybe it looks like this, and then we have a t of 1, and then maybe a t of 2, and something like this. That should probably be longer. I don't know. There we go. And we have this guy over here. And these arrows are just pointing the direction that the particle is traveling. So if you wanted to connect where the particle traveled, maybe it looks something like this, right? And I can see 2 x-intercepts. So again, not really a surprise if this does make some sort of circle or ellipse or whatever the heck that blob is that I just drew over there. What else do we need to do? So it crosses the x-intercept twice. Cool. So those are those 2 points right there. Write an expression that represents the distance traveled by the particle between the 2 x-intercepts. Oh, that's a fun one. So first x-intercept, and then the distance it travels is wherever we're moving around. And then to the second x-intercept. Do not evaluate. Okay, so this is all about the setup. Do not evaluate. Makes sense because, as you'll see, we'll be using a square root. Very hard to find the antiderivative of square roots with multiple pieces. So what do we need to do? Well, if we're looking for the total distance traveled around the circle, then that's all about arc length, I think, right? The length of that path. And so the first thing we're going to need to do is determine what time value starts us off and what time value ends us. And then once we know our time values, we can just use our arc length formula. Okay, well, in order for the particle to intersect the x-axis, and let's focus on this over here, and I'll show the 2 vectors. So here's my first one, and here's my second one. Well, this vector is a combination of both x and y movement. This vector is moving perfectly horizontal. So if it moves perfectly horizontal, what does it tell you about your y movement? Hopefully you're saying, oh, it's not moving in an upward direction at all. You're right. The y movement is 0. Or probably a better way to think about this is because this particle has two position functions, right? We have our x and our y. We know the x position will be a number. It's on the x-axis, but the y position will be 0. So I think to find this, we can probably set the y equation equal to 0. Add 2 sine of t, divide by 1, we get sine of t equals 1/2, and then you have to think what sort of triangles or know your unit circle make 1/2. We know sine is positive in the top 2 quadrants, it's the y, so if I wanted to sketch maybe 2 different triangles in here, should have done that in a different color, 2 different triangles in here, and we know sine is of course the opposite over the hypotenuse. That's got to be 30 then, right? The smallest one, 1 is 30. This will be square root of 3. So I think this is a 30 degree or pi over 6, which will make the red one 5 pi over 6. So we have pi over 6 or, of course, 5 pi over 6. Awesome. Now that we know where the x-intercepts occur, then we can set up the integral to calculate the distance between them. We do, of course, still need the derivatives of each function, but I think that's not too terrible. We're pretty good at this point. So let's find the derivative of the x component. So that's dx dt. Square root of 3 is a constant. Cosines become negative sign, but there's already a negative, so I think it becomes plus 4 sine of t. Of course, that's where that guy comes from. And then we also need our y component, so dy dt equals, and that's this over here, 0. The minus will stay this time because sine is just regular cosine. That's where the second guy comes from. And that's it. If you wanted to use your calculator, you could evaluate that. If you wanted to simplify a bit, you could, right? We have pi over 6 to 5 pi over 6, and you could say that this is something like 16 sine squared t plus 4 cosine squared t. You might be tempted to say, oh, that's just 1, but it's not. They have different coefficients, so I think that's not going to work for you, unfortunately. But either way, there we go, and that is all. The rest of today should be spent working on this assignment. It is nothing too terrible. It's mostly particle motion review, right? This one just says first derivative, second derivative. There are a couple tricks thrown in there, but I imagine it won't take you too long. Please do not use a calculator except for 10 and 13C, and I think those directions are reiterated as you move on down. And as always, if you do need any help, I have all of my solutions posted for you, fully worked out. So please let me know if I made any mistakes or if you need any further clarification, and I will see you back next class. I will note that there are no videos for the next 2 official days because it's just more vector practice. I'm going to throw some different questions at you in different ways, but really we're kind of done with our parametric and vector or particle motion section of this, so we're going to take a couple days to practice both some of my problems. As a reminder, many of these lessons are from the marvelous Nancy Stevenson from Clements High School in Sugar Land, Texas. Always important to cite your sources. And then we'll finish off with some AP style questions, and that'll be half of topic 4 done. Then we'll get into polar, which is really where the fun begins. Excited to have you back for that polar section. Keep up the hard work, and I'll see you in a few days.